Okay, this is exam paper Edexcel IGCSE Physics, which is used for the double awards, so it's paper 1. This is an older paper, we're just using it as a practice exam. It's using half an exam, which is the first 6 questions and question 9 added in because that's the topic we've recently studied. So this is really to show students what they need to do when they're revising, and it will take only an hour for students to do if it's half a paper. So if you do the full paper, it normally takes about 2 hours. So these are the formula that you're given in this Edexcel. As from this year, these are the only formula you've been given. So any equation not shown on this list, you have to recall yourself. Okay, so that's one thing you need to make sure you do when you're revising. Okay, so we're going to go straight into question 1. Question 1 is about waves. Okay, just making sure it's in view on the camera. I'd already started doing this, but my phone rang. Hopefully my phone won't interrupt me again. Okay, so it wants you to say which of these is longitudinal. Okay, now 3 of the waves are electromagnetic. Infrared, radio and ultraviolet are electromagnetic waves, EM waves. So it's a family of waves that light belongs to. They're all transverse, so that means they go up and down at right angles to the direction of energy transfers. Whereas longitudinal, like sound, one of the few ones, it's like areas of compression created when someone is creating any noise, a vibration. It requires a physical medium, and you would draw it as layers of the medium being compressed and other areas where they're stretched. So the wavelength, for example, for a sound wave would be the areas of the lines being close together. And the lines represent layers of molecules in the medium. So for example, when I'm speaking, it goes through to the microphone and it creates areas of compressions, and in between we call them areas of rarefactions. So sound is one of the main examples of longitudinal waves. So then they're going to focus, the rest of the question is on electromagnetic waves, and they're giving you a task where they're giving you 2 examples of electromagnetic waves: microwaves, infrared, which is basically heat radiation, so it's what you feel when on your skin when it warms up, and they want you to draw a straight line. So I don't know how strict they'll be in the exam, so you need to bring a ruler and do as they say, just to make sure you don't lose a mark for a silly reason. Link each of the electromagnetic waves shown, so these 2, to its correct hazard. So the things you need to know for the GCSE are uses of waves and also hazards. So the infrared can cause skin burns if you have too much. So that's like being in the sun for too long. The heat of the sun can burn your skin. And it's not the same as ultraviolet, which gives you a tan. The burning is due to infrared. Microwaves go deeper into the tissue, and that's why microwave ovens can cook a food from inside out. So the stress is on the internal heating of body tissue. It basically focuses on water molecules. Okay, so it has the right frequency to vibrate water molecules. So this is some good revision for you to go through the questions in this way. Okay, the next part of the question, part B, it wants you to look at X-rays. So again, X-ray belongs to electromagnetic waves, and you will know from just general knowledge that it's used for checking for broken bones. Okay, so cooking food would be infrared. You could use microwaves if you have a microwave oven. I don't use them. I prefer to use old-fashioned methods. Detecting forged banknotes would be ultraviolet, and smoke detectors are nothing to do with X-rays or electromagnetic waves, although they do use alpha radiation from nuclear physics, which you may have revised. Okay, so that's the beginning of question 1, and then it finishes with the last bit on electromagnetic waves, which is linked to part B, so it's B part 2, and it says which of these is used for infrared waves. Remember, infrared is heat, so cooking food is the answer. Okay, so it's actually using the same 3 of the same multiple choices as before. Sterilizing in medical instruments, that would be gamma radiation, yeah, which is similar to X-rays but produced by radioactive sources. So that's the first question done, and that's 5 marks, easy marks if you revised. Question 2 is on magnetic fields, which I recently revised with my class. If you're doing double science, it's not that big a topic, but you do need to know the details. So one of the required practicals or suggested practicals in the syllabus is to describe an experiment to investigate the magnetic field pattern around a permanent bar magnet. Okay, so here I've drawn a permanent bar magnet. It says you may draw a diagram to help your answer. So it's always a good idea to do that. So you do really need to have a ruler and a pencil to draw this. I'm drawing it in ink for the purpose of this video. Okay, so describing the method you would use is to show the shape. You can either use a compass, yeah, or you can use iron filings, which are tiny bits of iron, yeah, basically filed down bits of iron. So you could, as long as you use one of those, you'd be able to get the shape. But to get the direction, you would need to use compasses, yes? I'm saying compasses because you need to position them at different points around the magnetic field, like I've drawn, and the arrow indicates the direction the compass is pointing, which is always from north to south. So I've just drawn it at several positions to show that I know that you've got to use it at different positions around the magnet. And you can show this on your diagram as what I've said. So that's a good way of using diagrams. Okay, so a method, so describe an experiment means you have to write your method. So the method requires sufficient detail. For the 3rd mark of this question, you have to provide sufficient detail to describe the method more fully, such as any of the following. Place the compass in different positions, so you don't just say that the compass will show the arrow direction. You do need to mention that the compass is important for being able to tell the direction. So that's why I told my students I would use the compass method. I wouldn't use the iron filing method. The other thing about iron filing are that they can get stuck on the magnets and they create a big mess. Okay, I tend not to use this experiment with older students because normally they would have done this in year 8 or in key stage 3. So it says, here's another way you can get another mark, is to make sure you produce more than one field line. You shouldn't just do it one field line and on each side of the magnets, because you want to show that the pattern is symmetrical. The alternative way is you sprinkle iron filings on card above the magnet, so you don't sprinkle the iron filings directly on the magnet. So any additional detail could get you the 3rd mark, and this says tap the card to make the iron filings fall into position. That's how I've worded it, because if you don't tap it, the friction between the iron filings and the card will mean that they won't actually show the pattern very clearly, which is again why I prefer the compass method. So that's how you get your 3 marks. 1 for showing how you get the shape, 2 for showing how you get the direction, 3 for adding some detail to show that you know the experiment properly. Okay. They then go on in question 2 to give you 2 magnets next to each other, yeah, and then you have to complete the diagram to show the magnetic field pattern that they produce. Well, they produce 2 magnetic field patterns, if you like, that interact. Because the 2 south poles are facing, you're going to have repulsion, and in the middle you've got what's called the neutral point, yeah, where the lines are pushed apart, yeah. So in repulsion, if you had north and north, it would be the same, and if you had attraction, the lines would be different in the middle, and you need to make sure you know the difference in the field patterns. Now, how did they give you marks? Draw field lines for both magnets correctly. So obviously each one has its own field, and in the middle they get pushed apart, the field lines. Whereas if they were attracting, they would be like the 2 magnets would become one long magnet. The field lines would actually join up. So in this case, draw field lines for both magnets, 1 mark. Draw the field lines between the magnets correctly, yes. So they show that you understand the shape of a repulsion field. And then at least 3 field lines with directions shown between north and south. That's how you get the 3rd mark. Okay, so another straightforward question if you've done your revision. Okay. Next question is on irradiation of food. So it's then from the topic 7 on nuclear physics, radioactivity. The question is about food preservation. The diagram shows how gamma radiation is used to irradiate food stored in a wooden box. Okay, so they put the fruit in there. They use externally a gamma source to zap it, basically, and this radiation kills the bacteria, any bacteria on the fruit, because it has high energy. It's ionizing radiation. You don't need to mention ionizing, but they want to explain why gamma, the symbol for gamma is like this, is used instead of alpha radiation to kill the bacteria. Well, if you've done your revision, you'll know that alpha probably won't even get through more than a few centimeters of air. So it will actually won't have any energy to get through the box. So I would say alpha would not be able to penetrate the box. Yeah, gamma is more penetrating than alpha. So that's one mark for talking about penetration. Penetration means, as I put at the bottom, it means to pass through for those of you studying physics in English, which is an additional language for you. So therefore, only gamma can penetrate the box and get to the bacteria on the fruit. So if you can't get to the fruit, you can't kill them. Okay. Then the next part of the question then wants you to explain, that these fruits have been irradiated. Again, I don't really like this. It's better to buy fruit that hasn't been irradiated. But if you have to travel, if the food is taken around the world to be stored on shelves in the supermarkets, they need to have fruit that will last and won't go moldy straight away, which is what happens if the fruit is just left. So explain why fruit irradiated with gamma radiation is safe to eat. Well, the bacteria has been killed. That's one mark. They've actually told you, so you're just repeating what they told you in the first part. And bacteria, too much bacteria, if it's harmful bacteria, is not good for you. So it's safe from that point of view. But the fruit has not been contaminated is the second mark. They basically want you to know the difference between irradiation and contamination. Now, contamination is when some of the radioactive material is actually present. Well, there is no radioactive material present when you irradiate, because you're just hitting it with gamma rays which are coming out of the radioactive source. So in other words, the fruit has not become radioactive by irradiation, which is sometimes confusing for students. Irradiation just means that the radiation hits something like a bullet hitting something. Once the bullet's been hit something, it's no longer dangerous. Yeah. So once the gamma radiation has killed the bacteria, there is nothing radioactive left inside the box. The radioactive substance in the question, if you remember it, was outside the box. The source itself, the gamma source, does not get anywhere near the fruit. It's just this dotted line which shows the gamma rays are traveling and doing their job on the bacteria, and then the box can be then sent away to supermarkets, etc. So this is what, in other words, the fruit has not become radioactive by irradiation, and because the radioactive source itself has not been in contact with the fruit. It's only the gamma rays which have been in contact with the fruit. So I think that first 2 points will give you ticks, but if you've made the detail given in the third and fourth lines in my answer, they possibly will give you the mark as well. Okay? All right, so that's the end of question 3. Question 4 is probably taught in year 10 in most schools. It's topic 1, which is forces in motion. This is about stopping distance on a car. A driver sees a hazard on the road ahead. Yeah, the graph shows the velocity of the car in meters per second from the moment when the driver sees the hazard. So from time 0, he sees the hazard, he's going at 15 meters per second, and he keeps going at 15 meters per second. Why is that? Yeah, because it takes him time to react. Yes, use the graph to determine the reaction time of the driver. So the reaction time of the driver is that dotted line where they've drawn it, and they purposely not put it exactly at 1.0 seconds to see who is paying attention to detail. And to get the mark, you need to put it as 0.9 seconds. Once you do that, you get the 1 mark. The second part then says calculate the stopping distance. So for stopping distance, there's 2 bits to stopping distance. Stopping distance equals thinking distance. The time it took for the driver to think, he's still traveling, so he's moving a distance while he's thinking, plus braking distance, and that is a 4-mark question. Now, you need to realize, so thinking distance is from the reaction time part of the graph, and that, if I can just draw a squiggly line, it is the area of this rectangle. That's the distance traveled, the area under the velocity time graph from 15 seconds for 0.9 seconds. That's what he's doing. The braking distance is when the brakes get activated, the car starts slowing down. So that's from 15 seconds down to 0. So it's the area of the triangle I've just shaded in. So braking distance is an area of a triangle, and thinking distance is the area of the rectangle. Okay? So the total distance is the total area underneath the line of the graph. Okay, so that's what they want you to know. So as long as you give one of these points, you've already got a mark without doing any calculation, that you know that the distance traveled in the velocity time graph is the area under the graph. If you think about it, you're multiplying meters per second by seconds, so that means the meters per second multiplied by seconds means the seconds will cancel out, and that will equal meters. Okay, so up to 0.9 seconds first is the thinking distance, remember? So 0.9 seconds, the thinking distance, is equal to 15, the speed, the velocity, times 0.9, that comes out to 13.5. So you get a mark for calculating that. And then the braking distance, the area of the triangle. And if you know, a triangle's area is half base times height. Well, the base is the time, which is 3.1 seconds from 0.9 to 4.0. The speed starts at 15. Yes, so it's half the base times the height is 15 in terms of the velocity, the maximum velocity of the graph. If you divide that by half times 15, is basically average speed would be 7.5. Yes, so it would be like that. And basically that rectangle would be the same as a triangle, which is why a triangle is half the area of the rectangle. Okay, you do that, you'll get 23.25. You add those two together, you get 36.5. So one for knowing the concept, distance under the graph, one for working out the thinking distance traveled, 13.5, and one for doing the area of the triangle, the braking distance, as 23.25. So I would put it that accurately, but you could round it up to 36.8 if you wish to, and you probably still get the marks. So that's how you get the 4 marks. They then ask you to calculate the acceleration. Well, it's actually a deceleration because it's slowing down. Okay, and that's a crucial point, that you realize it's going down from 15 to 0. So speed is reducing as the brakes are activated. Basically, the work done by the brakes goes into loss of kinetic energy and causes heat. So that's from an energy point of view, if they ask you that kind of question. But acceleration is change in velocity, which is a decrease. So the decrease in velocity is minus 15. And the time taken for the braking, remember, was 3.1 seconds. Yeah, the second part of the graph. You do that together, the minus sign shows that you know it's a negative acceleration. So acceleration minus means deceleration. And the units have been given to you, so I don't need it. So 3 marks, 1 for knowing the equation, 1 for putting the numbers in, and 1 for the answer with a negative sign. Okay, there's your 3 marks, and that is rounded up to 2 significant figures. I hope that makes sense. So that's a good practice of forces in motion, well, the motion section of forces. Okay, the next part is still on the same theme. It's talking about the speed of the car, affecting both the thinking distance and the braking distance, but they want you to now discuss or list other factors. Discuss is more than list. I've listed them, and I think they'll give you the mark based on the mark scheme. That affects thinking distance. I've put thinking distance on the left just for the sake of this marks, my model answer. Students probably will write 2-3 lines on each as paragraph or as sentences, but you don't have to. You could do bullet points, okay? So, and the breaking distance would be this list. So they want 4 marks, so you should give 2 for thinking distance and 2 for breaking distance. They don't want you to just think about one of them, but they want the answer says and the breaking distance. So anything that causes the driver to slow down his reaction timing, like tiredness or his age, a young person would normally have a faster reaction time, or the use of anything which slows down the brain, alcohol, drugs intake, even medication, or a distraction, for example, a phone, being on the phone or listening to, or phone ringing could be a distraction. Any of those would affect the thinking distance, because the thinking distance is to do with reaction timing, okay? And then the braking distance is more to do with friction. So the condition of the brakes, if you've got bad brakes, they won't work as well. The brakes are too old, the pads are worn, etc. Conditions of the road, for example, an icy road, yeah, so it could be icy or wet. Those would affect the braking distance of the car. The condition of the tires, if the tires are worn out, again, that's a friction issue. So remember, this is friction, icy, wet roads, friction, tires, friction, and this one is different, slope of the road. So if you're going down a slope, obviously the brakes would have to work harder because the car would want to speed up at the same time. So any of 2 points from either list will get you the 4 marks. So you could 2 of these and 2 of these, you'll get your 4 marks. Okay. All right, next question is on springs, stretching a spring. Well, that's called Hooke's law. And for those of you who know the equation, the extending force, the force that you apply to a spring, is equal to the spring constant, or the stiffness of the spring, times the extension. Okay? So that's the equation to revise. It doesn't come up in this question, but you might as well know it. The graph shows how the extension of the spring, yeah, here, varies with the force applied to the spring. So they put force on the horizontal axis because that's the independent variable that normally goes on the horizontal axis. So that's the independent variable. When you change the independent variable, the dependent variable is the extension or the new length, which you would have to measure to work out the extension. The line in the graph shows that the spring has been extended past its elastic limit. Now, if it's gone past its elastic limit, they want you to know that it will not return to its original length. So the original length would be where the extension is 0. So they're giving you information, so I've underlined it. This is called active reading. When you read a question, then make sure you underline key words so you're thinking about it. So it says the line has a straight section. So the straight section is up to here, yeah? And up to that point, Hooke's law applies because it's a straight line part of the graph. So Hooke's law only applies up to the straight line portion. So it's got a straight line section and then a curved section. As you can see, this is the curved section here. So I've drawn, when it's gone past this elastic limit, it becomes curved. So you should know that for when you revise. They're not going to ask you all about that, but the first thing they want you to draw is a cross on the line to show the elastic limit of the spring. That's the point beyond which, if you stretch it beyond the elastic limit, it will no longer return to 0 extension when you remove the force. And the elastic limit is slightly further than the straight line portion. Okay? It's not exactly on the straight line portion. So as long as you've got the elastic limit somewhere between the straight line portion finishing and not the end of the curve, I wouldn't put it, so somewhere in that region you will get the mark for knowing that the elastic limit is just past the proportionality limit of the straight line part of the graph. Then it says, sketch another line to show how the extension will change when the force is decreased. So if you decrease the force back to 0, yeah, what will happen? Well, because it's gone past the elastic limit, it will get shorter, obviously, when you remove the force. But because, if say you draw it parallel to the original line, it could go back that way because you're removing the force. You start from there, it will try to get shorter, but it will leave it permanently stretched, yes, because it's extended past this elastic limit. So the second line is you're going back to 0 on the force, and showing that it has or it still remains stretched, and that's why they give you 2 marks for that. Okay, so 1 for showing that it will hit this axis at a value greater than 0 on the extension, so we'll have a permanent stretch on it, and you basically damage the spring. It then wants to talk about what's happening. Well, what's happening is it wants you to know what type of energy, state it, don't need to explain it, state which energy store of the spring increases when it is stretched. In other words, what energy does a spring store in it? Yeah, so a spring is like an elastic band, stores elastic potential energy. That's the only way you can get that mark. Okay, then ask, this is now energy transfers topic. How is this energy transferred to the spring? Well, we were doing physical work on it. Physical work means force times distance. Yeah, that's the work done. So physical work. Whenever anything does physical work, we say it's a mechanical energy transfer. Okay, we didn't do it electrically. We didn't do it by heating. We didn't do it by radiation. Simply by reading those 3 words, I think common sense would tell you that we need to tick or cross the mechanical method. So again, you need to make sure you revise the energy topic. By the way, the energy stored, if you put the graph sideways, it would be, and the force is on the vertical axis, the energy stored would be the area under the force extension graph. Okay? That's question 5 done. Question 6 now goes into electricity. So this mock covers quite a lot of the main topics of the course. Yeah, the only topic that's not covered, I think, actually 2, solids, liquids and gases, doesn't really go into it, although when you'll see, the only topic other than that we haven't covered is astrophysics, partly because that's the last topic and some students haven't yet covered it. So here the student investigates. So another investigation skill, how current varies with voltage, yeah, for how the varies with a filament lamp. Sorry, I just got distracted by my phone. Okay, so filament lamp, the symbol for a filament lamp is a circle with an X in it. So draw a circuit diagram, a diagram of the circuit that the student could use for this investigation. So first of all, obviously you need to have a power supply, you need to have the lamp, you need to measure the current, yeah, and you need to measure the voltage. So if you got so the voltmeter is, you need to add the voltmeter correctly. So I would tell my students, always do your circuit. So I've used a battery. So this is a battery, means more than 1 cell. This would be a cell, but when you have dotted line between 2 cells, that would be a multiple number of cells. Always draw your full circuit without the voltmeter first, yes, because that is the actual part where the current flows. You don't want the voltmeter in series with the bulb. So you then need to add the voltmeter across the component that you're investigating. And in this case, it's the filament lamp, which is the X. So the voltmeter correctly should be drawn over the circuit, and that's why I wanted to draw it while I was talking to you. So if you got all the symbols correct, yeah, that means the power supply, the filament lamp, the ammeter in series, so the ammeter goes in series and the voltmeter goes in parallel. So you get 1 mark for putting the voltmeter in series, 1 mark for putting the voltmeter in parallel, 1 mark for ammeter being in series. So there's your 3 marks. And then the 4th mark, which you don't need to put in for the first 3 marks, is to have some way of varying the voltage. So I've put a variable resistor in series with the power supply. Yes, so if you put the variable resistor to the 0 setting, the minimum setting, then the bulb will get more voltage. If you take some of the voltage, it will reduce how much you give to the bulb. So this is a method that you could use to reduce the voltage, so you can investigate the variation of voltage with current, or current with voltage. Okay, so the next thing they want you to do is to explain how to do this experiment. So very simply describe a method. So again, you see that there was a one for magnetic fields. Now they got a method for doing an investigation on the bulb. So investigation skills are crucial for students to get full marks. So it's just a logical sequence. Method means a logical sequence of what the student could do for this investigation. So describe a method that the student could use for this investigation. So always tell students to set the voltage to the desired value first, and I always start with 0, although that's not in the mark scheme, and then move it up to the maximum. So this is just basically, in a nutshell, the way to do this experiment. So then you measure or record the voltage and current readings using the ammeter and voltmeter. So as long as you're recording, that's one set of data, you'll get 1 mark because you're looking at the current and the voltage. But of course, that's not going to tell you how it varies. Remember, the aim is to investigate how current varies with voltage. Well, for voltage to vary, yes, well, you need the variable resistor in there. Repeat for different voltages. You don't have to say how. Measuring current each time. So you have to vary the voltage. So as long as you've mentioned that you have to vary the voltage and then measure the current each time, you'll get your 2nd mark. I then say plot a graph of voltage against current. Obviously, a graph allows you to see the variation of current with voltage visually. Okay, that's why you always plot a graph. It's a visual representation of the answer to the question. And then you can get extra marks for saying things like this. Either of these, repeat and average readings for each voltage. And I've said to get reliable data. Yes, that's why you repeat and average. So you could get a mark for this one, or you can get a mark for saying switch off the current between readings so you don't have another factor influencing it. So this is, in a way, is a controlled variable. Yeah, you don't let the current just keep going on. It's also is a normal practice with electricity experiments. So that's how you get the 4 marks. That's the order I would write them in. I think the mark scheme's written them in a slightly different order. Hope that makes sense. It's a very common investigation, either with a bulb or a diode. You would need to know how to do it with a diode and a fixed resistor. Okay, so the method could be very similar in basic terms. So that's question 6. Start of question 6. Then it goes on to saying the student then extends the investigation, or at least the analysis of the investigation, by recording additional data for the lamp. Well, obviously they had voltage and current readings. You see they've gone up in steps of 2. That was what they did. Nice intervals, so that's the variation of voltage. Recording the current. Ideally they would have repeated an average to see if the current value was the same each time. Now, if you hadn't switched on and off, maybe that it would heat the filament lamp and the heat would change the current each time. So that's one reason why you switch on and off the current between readings. Okay. Now, in this case, this was a method for the student. For each voltage, they actually switched on the current for a fixed amount of time. So in a way, that is also a way of having a controlled variable. Okay. Fixing one variation to at least know that exactly how long they left it on for. They then recorded the current and the color of the lamp. Now the color of the lamp is linked to the final question, which I've removed because it's actually linked to astrophysics as well, because the color of a star is linked to the temperature. So I think that's what they're getting at. But since we weren't revising astrophysics for this mock, I removed the final part of this question. Okay, so they've done that, and then they calculated power, yeah, which is voltage times current, and then they calculated energy, which is power times time, which would be this value times 45 seconds. So if you have no power for 45 seconds, it will still lead to that. So you'll notice this times 45 should give you that. Okay, there's a question on it in the next part. It then wants you to state the unit for current. Well, current is amps or ampere or amps. You could also write milliamps. Yeah, often I get my students to measure in milliamps, so they get more significant figures when they're reading it. Sometimes if the component has a high resistance, you don't get much current. So this, presumably, that's in amps, but they don't tell us. They actually haven't told us, whereas all the others have given us the voltage. Okay, so they haven't given us the unit because they want you to put the units in. So the current should be amps, but it could be milliamps, okay, as they haven't stated it. But by calculation, we know that's amps because when you multiply the voltage by the current, is 4 times 0.9, it gives you 3.6. So that's how you get the power, voltage times current. Calculate the missing energy value. So they want you to work out what number should go in there. Okay, so then again, you need to know the equation. Yeah, and let's look at the equation sheet from that I showed you at the beginning, and you'll notice that this is the first equation on the list. Energy transferred is current times voltage times time. Okay, so you don't need to remember that I is current, V is voltage, T is time. Okay, so going back to this question then, you need to do exactly what it says. Energy is V times I times T. The reason I put V times I in brackets to show you the power is V times T. That allows you to go use the calculation already done for you for 4 volts. Remember, you're doing for 4 volts. So you want to look at this line. This multiplication is already done. So power multiplied by 45 seconds. And you'll get the energy. So 3.6 watts times 45 seconds gives you 162 joules. And I think I was generous with 1 or 2 of my students. I just read the mark scheme and they've told you that they want it to 2 significant figures. So if they say they want it to 2 significant figures, you then need to round it up and say it's 160 joules. So you get 1 mark for getting 162 and 2 marks for getting and recording it as 160. Okay? Hope that makes sense. So that's the end of the electricity part of the question. And this is the final question, which is on nuclear reactors. So this is topic 7, so the penultimate chapter. Here you got a nuclear reactor. The inside is the workings, and you've got shielding on the outside. You've got control rods in there, moderators in there, and the fuel rod as well that is in the reactor. Okay, so the coolant in and out is water, where it takes away the heat, which then turns a turbine, etc. It boils the water. So it's a very complicated way of boiling water, in effect. Okay, and from that steam power, you can turn a turbine to generate electricity. So each part of the nuclear reactor has a function. So you've got the function and is made of a suitable material. Yeah, complete the table by giving the missing information. So you get basically 5 marks, 1 for each of these boxes. 1, 2, 3, 4, 5. Okay, and you've got to fill them in. So control rod absorbs some neutrons. Now, if you remember nuclear fission, this is a nuclear fission reactor. It produces, every time a nucleus splits, it releases some neutrons. If there's too many neutrons, the reaction will go out of control. So by absorbing some neutrons, it controls the rate of reaction and keeps it safe. And they use boron for that. So 1 mark for knowing the absorption of neutrons is what the control rods do. Okay, moderators moderate, which means they slow the neutrons down. So believe it or not, they actually need to slow them down to make them cause the nuclear fission reaction to occur. If they're going too fast, they tend not to work as well. And for this they use graphite. So this is to slow neutrons down. Any words to that effect will give you the mark. Then the shielding on the outside, is normally concrete. Probably, if I was designing it, it would be concrete with lead lining inside it, because those are dense materials and you want to stop radiation from escaping to where people are. Okay, so shielding prevents irradiation and for any of the radiation to escape. And of course, if there's a nuclear disaster, the shielding can crack and can not only cause irradiation, but it can also cause contamination if some of the radioactive material escapes. And I would use concrete lead. They've also in the mark scheme allowed people to say steel, because steel probably would also help with that. They've also put water in there, which I haven't included. Okay, so I think they're being quite lenient with the marking of this question when they did it. But to me, it should be concrete lead. Okay, and then the fuel rod. Fuel rod is where the fuel is. Well, in this case, the fuel is uranium normally, and it's uranium-235. As long as you got uranium, or plutonium, which is man-made, you can have plutonium reactors as well. The one that we've used with students to explain this process is uranium-235. As long as you got uranium or plutonium, they'll give you the mark for the fuel. and they want you to explain, well, what is the fuel rod? Its function, what is the function? It's a material that will produce nuclear fission. So you must have the key word, the material that will produce nuclear fission for that mark, that mark, that mark. Gets you the 5 points. Looks like my green ink is running out. Okay. All right, so that's the beginning of question 7. And finally, the last page of this mini mock, half a mock, is about isotopes. Heavy water is a compound of oxygen and an isotope of hydrogen called deuterium. So we're looking at hydrogen called deuterium. So isotope of hydrogen, they don't normally call an isotope with a different name, but because hydrogen was one of the first ones, as lightest elements, the hydrogen isotopes actually have names, other names. Deuterium means hydrogen with an extra proton. So they want you to say that they're telling you deuterium is formed by the fusion of protons. Okay, so what happens is one proton collides with another proton, and then they actually become a proton-neutron combination. Yes, so one of the protons changes to a neutron. And then finally, you need to state the meaning of the term isotope. And as simple as that, you need to have the same number of protons and a different number of neutrons. That's the only way to get the 2 marks. It then wants you to explain the difference between nuclear, and I've put these in bubbles to make sure you know it's nuclear fission and nuclear fusion, because 1 or 2 students were confusing nuclear with atoms. In radioactivity, we only deal with the nucleus, we don't deal with the atom. Okay, so explain the difference between them. Fission is splitting of a nucleus. So if you put splitting of an atom, it's not going to give you the mark. And fusion is joining or fusing of 2 nuclei. Don't put atoms instead of nuclei or nucleus. Nuclei is the plural of nucleus. Okay, means it comes from Latin, I believe. Okay, then state a location where nuclear fusion takes place. So stars is where nuclear fusion takes place. Okay, now they haven't done the rest of this topic yet. Okay, so I'll get back to you, and if you read that. Hello? Yes, I understand. Okay, but I've been trying to get hold of you